Hey, so today I'm going to go through my neural network program. I've made it in Java from scratch, so I'm going to talk about the different parts of it and show you how it works. So the program has four different parts. This value part contains the code for the base data structure, a value object, which is basically just a wrapper for a double with some extra stuff. Then we have a layer, which is basically a matrix of these value objects. Then we have the network, which contains all the functions for backpropagation, going through the network training process, taking the loss of the output of the network, and also methods for saving and uploading pre-trained models, so you can use those. And then the tester is just where we test out all the functionality from these previous three just to make sure everything works. So let's take a look at the value. So as you can see here, the value code is pretty simple. There's not much to it. The main chunk of code is this back code. This is all of backpropagation, basically, because while the code for my network is matrix based, networks are processed with matrices going through the network. The backpropagation all happens on the individual value level. So what happens is it gets called recursively. So if you call the back function for a layer object, it recursively goes through and calls the back function for all of the value objects stored in that layer object. So you can see basically what it does is it checks what the operation was of the values that created this current value that you're trying to backpropagate through, find the gradient of. And how it does this is whenever you do arithmetic with value objects, it creates an array of the two value objects that created the new value object through the arithmetic, and then also stores as a string a symbol that just represents what operation was used to create the new value object. So each value object has stored within itself an array with the two objects that were used to create it, the two value objects that went in to create it through arithmetic. And if there's no arithmetic that went into creating this value object, it was just created, then this stuff is just blank and there's really no effect. But what happens here is with the backpropagation is it sets the gradient for these previous neurons based on this operation. And then basically this is just simple derivative rules for the different operations. And then for some of the other ones, like this is for the derivative of the ReLU function, and for the hyperbolic tangent function, their derivatives are special. So yeah, and then you can add, depending if you're using different kinds of activation functions, then I can always just add another one onto this, another option for this little string showing what the operation was, if I wanted to do that. So it's pretty modular. Alright, let's take a look at the layer. So the layer is, like I've said before, basically just an array or a matrix of value objects, and it can be one or two dimensional. Most of the time it's just going to be a one-dimensional array, because that's going to be for your bias and your neuron layers. the only time where it's going to be two-dimensional is with the weight layers, just because of the matrix math for that. So really the most important part of the layer program is the arithmetic functions. So it's basically the same as with the value. It's very important implementation because the way I've programmed the network is that the forward propagation is all just using these layer objects instead of just pinpointing individual values. These neurons help group each layer. So you have a layer object representing all the different neuron layers, layer object representing all the different bias layers, and neuron object representing all the different weight layers. So these arithmetic functions, these operation functions, are very pivotal in forward propagation through the network. And finally, that leads us to the actual network code. So as you can see, when you initialize a new network, and this is using an array of neuron layer dimensions, it will automatically create the weight and bias layers based on what you want the dimensions of each neuron layer to be through the network. You can specify how many neurons in the input, how many neurons in the output, and how many neurons in each hidden layer. And then it will automatically create all the other weight and bias layers for you. There's also the other option to upload a string containing all the weights or the parameters of a pre-trained model. So that's very useful because you don't want to have to train a model every time you want to use it. Especially if you want very high accuracy, it can take a while to get that through training. So I've programmed a way to actually save the model. If we go down to the end of the program, there's the toString method for the network, and that just creates a string that lists the dimensions and all the parameter values in the network. So then you can just take that string and use that as the argument, the parameter in the network initiation, and that will put in all the pre-trained values, pre-trained parameter values into the network, so you can use a pre-trained model. Okay, so now let's look at the tester. Let's test out some of the functionality that I've created in this program. First off, let's test the gradients. So the gradient, or also known as just the derivative, of each of the parameters is found using that back propagation method in the value object class. So what we're going to do is we're going to run this method here, and it's going to have all these values, which are going to, it's like a little mini network, and all these values are going to go to O, which will be the final output. And then you can see we just do O.back, which will go all the way back through all the values in the network and populate them with their individual gradients. So then what we can do is we can get the gradients, or how much effect each of these parameters had on O, the final output. And it should be these values if you found them using just normal calculus. These would be the numbers you get, but we're going to see what we get through our model. So after running it, you can see if we compare, these values are basically the same. We have 1, it's 1. Should be 0.5 is 0.4999, basically 0.5. Same with B, 0.999, 1, close enough. Negative 0.4999, basically negative 0.15, 1.5, sorry. 0, it's 0, 0.5, 0.49999. So this shows that our backpropagation method is working correctly. Now let's take a look at another very important part, which is the matrix arithmetic, because it's very important to make sure that our our matrix math is correct if we're having matrices representing different parts of the network moving through the network. Because if the math is wrong in combining them, especially with matrix multiplication, because it's not very straightforward, it's not like taking the dot product, which is where you just element-wise multiply the two matrices together. Matrix multiplication is a little bit tricky, so I just coded a little bit of an algorithm to do it. I don't know if it's the best, most optimized, but it should work in theory, so we're going to test that out and see what happens. Alright, so this is our output from printing the data from this layer that was the product of these two layers here. So you can see this is the first row, and this is the second row, and each of these are columns. So let's go online, use a online matrix calculator to double check to see if everything's adding up correctly. Alright, so these are the matrices that we had in our program. So let's multiply them and see if we get the same thing we did before. So we get 28, 24, 30, 21, 15, 17. Let's check to see if that's what we got. So as you can see, our program output, we have 28, 24, 30, and then in the second row, 21, 15, and 17. So it looks like our matrix math is working correctly, so that's all good. Now let's move on to the final step. Now finally, we are going to actually run the network. So this first line of code here creates the links to the network layers. So it's going to have an input layer of 2 neurons, then one hidden layer of 4 neurons, and then an output layer of 1 neuron. And our training data is going to be an XNOR logic gate. And in case you don't know what that is, I'll show you. So the XNOR logic gate is this right here. It's a logic gate. If you know what a logic gate is, it has to do with Boolean algebra like and or, stuff like that. This is just a more complicated kind of logic gate. So if we have 2 zeros or 2 ones, then the output will be a 1. But if we have a 0 and a 1 in any combination, then the output will be 0. So this is our very, very simple training data. Of course, the model doesn't know this. You could create a function where it's just, if there's 2 zeros, give us a 1. If there's 2 ones, give us a 1. However, we want to train a model, and this is just a very simple data set that we can use to accurately train a model very fast, just to see if it's actually working. So what we're going to do is we're going to split this data set into input and output. So we're going to have a pair of zeros as input, and the matching output will be 1. And then so we're just going to pair these, the A and the B's, and then have matching output. And then we're going to run that through the network, and it's going to go back and refine until it's accurate. So let's see what that looks like in the code. So in the code, you can see that we have the training inputs, and then their matching outputs. And then here we have the string. Like I mentioned before, we have the function that allows you to save all the parameters of the network as a string. So that's what I did before. I pre-trained the network to be at this accuracy, and we're just going to use this string to create a new network, so then we don't have to go through the training process all the way from scratch. And then what we're going to do is I created a while loop which will go until the loss gets below this value. So we're starting from the loss here at this very, very small number, and we're going to make it even more smaller. We're basically going to go through each training example, run it through the network, and set the output into an array of the network outputs, so then we can use that array later to evaluate how well the network did. And that's what we do here. We get the loss, the value of the loss, by using the loss function. And for every 100,000 iterations, we're going to print out the loss. If we print out the loss every iteration, it would just be way too much. So we're going to do every 100,000 iterations. So there's a lot of iterations, but every 100,000 iterations will print out the loss just so you can see the number getting smaller and smaller and smaller, because that's pretty satisfying to see. And of course what we're going to do is just set the gradient to 1 for the final variable, just because the gradient's 1. Then we're going to use the backpropagation method from this loss value, and that's going to go back through the network and set all the gradients for all the parameters, and then we use that to do gradient descent, which is where we adjust the parameters a little bit by using their gradients to make the output more accurate. And then finally we're going to print out the output to see how close it is to what it's supposed to be, and we'll also see the time it took to train the network. So let's go ahead and run that. Okay, so now you can see it's training, and it's actually coming out pretty fast for this executing every 100,000 iterations of that loop. It is crazy how fast they're coming out. That just shows you how insane computers are. But it might take a bit, so we're just going to speed things up a little bit. Alright, so our model just finished training, and now we can see the outputs. So this is supposed to be 1, and we have 0.9999. That's pretty good. It's supposed to be 0, and we have a very, very small number, close to 0. This is also pretty close to 0. And then finally, this is supposed to be 1, and it's 0.9999. That's pretty good. And then as you can see, this is the string with all the parameters with this newly trained model. So we can just save the string and then use it to re-upload if we want to have this more accurate model in the future. And that took 129 seconds to fully train. Thanks for checking out my neural network. It's very simple, very rudimentary right now. But I'm going to work on adding a lot more functionality, processing a lot more complex data,